Okay, so last week we covered chapter 2 and we talked about different types of equilibrium. When we were talking about equilibrium last week, what's the simplest definition of equilibrium that you can think of? Like if you had to distill it down to like one big idea.
Net force 0.
Oh, very nice. The net force is going to be equal to 0. And so anything that has a net force of 0 is in equilibrium, and there's a couple different types of equilibrium. The one that we talked about to begin with, if you have an object that's sitting at rest on a surface, a chair or a table or something like that, the floor, then what are the forces that we have working on this? What's pointing downward?
B, gravity.
Gravity, the force of gravity on the object, which we call weight. And then has to be, in order for this object to be at rest, there has to be a force balancing the weight, and that is the normal force, or the support force coming from the table. And I'm going to label that with an N for normal. And so the normal force is upward, the weight is downward, but they're the same magnitude. And since they're the same magnitude, then the net force equals 0 applies. Do you remember what kind of equilibrium this was?
It is static.
It is static. So since this object is at rest, this is called static equilibrium. And then we had a case of, I'm going to just use another box or some kind of crate. We're going to talk about that guy pushing the crate today. And so he's applying. Now our crate is resting on the ground, so does it have these same two forces acting on it? It does. So it has a weight acting downward. It has a normal force acting upward. He's going to be pushing to the right. But he's going to be traveling at a constant velocity. He's going to push it in a straight line. The speed is going to be maintained. This is a typical way you would push a crate across the floor. Normally when people are pushing crates across the floor, they're not trying to get faster, 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 so they have to run behind it. And they don't want to let it slow down because once you stop it, it's hard to get it started again. So he's going to want to keep that force steady, and it's going to balance what force that's acting in the opposite direction?
Balance, of course, friction.
Yeah, so the balancing force for the push has got to be friction. There's got to be a force balancing out the push in order for this thing to maintain a constant velocity. So we have the normal equal to the weight. We have the push force equal to the friction. And that means that our net force is 0. So this type of equilibrium was what type?
Dynamic.
Dynamic. Very good. Okay, so dynamic meaning moving and static meaning still. So those were our equilibrium situations. No, the big idea when the net force is 0 is there is no change in motion. So this was what the first law was about. Are both of these objects experiencing inertia? Is everything with mass have inertia?
Yeah.
It does. So this object that's at rest, definitely a good inertia example. It's at rest, it's going to stay at rest until some force comes and acts on it. This is not at rest, but is it going to have a big tendency to keep moving once he lets go of it?
Assuming friction is still there, it would stop.
Yeah, if the push suddenly went away and he took his hands off it, the friction is going to keep acting while it's moving, and then it's going to bring it to a stop really quick. So we're pretty familiar with moving heavy objects across floors. If you pull a sofa or you're lifting and dragging a table, it's not like that thing's going to go whee and keep moving, but that's because when we're pushing against friction, there's really not inertia at work in that case, because there is a net force that's going to be applied when we stop pushing, and that's friction, and then it's going to stop. The better examples of things that are moving at a constant velocity that have a tendency to keep moving at a constant velocity would be a bowling ball on a bowling lane. If you don't want to get in the way of the bowling ball, it would hurt you if you put your hand down or stuck your foot out and tried to stop the bowling ball. That's got a lot of inertia. It's very massive. It's moving in a good clip. Something that's got a lot of mass behind it, like a freight train. You wouldn't want to get in the way of a freight train and be like, stop freight train, because it has a lot of inertia. It's not going to slow down for you. And then we talked about the space examples with the movie Gravity, and obviously if there's no friction at all and you are out in space and there's nothing to hold on to, any little push will get something moving. If they drop their wrench, it's just going to fly through space and keep going forever and ever until it bumps into something. Okay, so that's the review of last week. What we're going to do this week in more detail is we're going to be changing these forces so that they're not balanced anymore. And we're going to be putting little, not equal lines. Most of the time the normal and the weight are going to be equal for all the examples that we do. I'll talk about a couple that are not the case. But let's go ahead and move on and talk about some unbalanced forces. So Newton's first law was that objects continue in their current state, either at rest or at constant velocity, unless acted on by a net force. Newton's second law is really just an equation. That's all it is. If you want to create some sort of change in motion, you have to use a net force. So we talked a lot about acceleration and changing velocity in the last unit. We did all that good math. But in this unit, what we're going to find is what is causing the acceleration. So changes in motion are created by a net force. So all the examples we did last week where there's zero net force, we didn't have to worry about that. We discussed the changes in motion at the very end of class. Net forces are that's what's creating our acceleration. So every problem we did in the last unit, in the linear motion packet, and on the test that you took, if there was a change in velocity, if you're a Ferrari or a Corvette accelerating, if you're a hummingbird, if you're somebody throwing something up in the air to try to reach a window above you, in all those cases, net forces were applied to objects, and that created an acceleration. Sometimes the net force that was applied to the object was just due to gravity, and that was it. But sometimes the net force was applied by a person or a car engine or something like that. So Newton's second law is the relationship between the net force and the acceleration and the mass of the object. I'm going to write the very science, mathematically proper definition. And I'm just going to write the equation and tell you how they're related. Actually, hold on, I'm going to erase this and start off different. I'm going to start with the word acceleration instead of net force. Newton's second law. Acceleration is directly proportional to net force and inversely proportional to mass. There's a lot of math going on in that definition, and it sounds and looks a little bit confusing. I'm going to write it out in mathematic equation way. This is what Newton was so good at doing. And I'm going to use that net force and M. This is one way we can write the equation for Newton's second law. Newton's second law is sometimes called the law of acceleration, just like we called the first law the law of inertia. Galileo did all that great work with his inclined planes in his beautiful Italian villa, rolling things up and down hills, measuring velocities, and looking at how distance was covered over time in different ways. And he did a lot of work and collected a lot of data that talked about acceleration. What Newton was able to do was to take his work and expound upon it and make more sense of it in terms of forces applied. Why is the ball rolling down the ramp? And why does it accelerate on the way down the ramp and then decelerate on the way up the ramp? And he attributed all that to components of the gravity that are acting on the ball. So he was able to take the ideas that Galileo started and formulate them into this really pretty mathematical relationship. This is what Newton came up with based on his own studies and on what Galileo had done. The directly proportional thing I want to talk about, the directly proportional and inversely proportional, because sometimes those phrases scare people. And if you haven't had a math class that talks about this in a while, they can make you feel a little unsettled. So let's discuss that. If I double the net force acting on an object. So let's just give a good example. I'm going to have somebody and they're going to be pushing a shopping cart. There's my buggy, as we call it in the South. I'm smiling because I'm shopping in Publix, my favorite grocery store. And in my shopping cart, I have some groceries. Got a few things piled up here, some cereal and some milk and some cans of food. And there's some stuff in there. And I'm going to push my shopping cart with a force of 10 newtons to the right. So let's say that then I look at my watch and I'm like, oh my gosh, I gotta get home and tutor a student. So then I change my force and I push it with 20 newtons of force instead of 10. If I double the force that I apply, what's that gonna do to the acceleration of the cart?
Increase the acceleration.
It's gonna increase the acceleration. And you can do a little trick called the rule of ones. This is a neat trick. With the rule of ones, we put in the change to the force and we put a 1 in for everything that's not changing. So the items in my cart aren't changing, the mass stays the same. The force is changing. So I'm gonna just say A equals, I'm doubling the force and then the mass is staying the same. So if I double the force and the mass stays the same, 2 over 1 is equal to 2. So that means that the acceleration is also doubled. These are the sorts of conceptual questions that you're going to be I'm going to be asking on the test, and you're going to be answering. If I triple the force, what happens to the acceleration? It's going to triple. So directly proportional means whatever you do to the one component, the same thing happens to the other component. So if I cut the force in half, I'm going to half the acceleration. If I quadruple the force, I'm going to quadruple the acceleration. Does that make sense? Okay, so that's how the directly proportional part works between acceleration and net force. I like writing the equation this way because you can see this is on the top and that's over here. It makes more sense to me written this way than the way I wrote it on your assignment sheet, the F equals MA way. I think F equals MA is a great equation too. It's the same equation. The M is just multiplied over. I just don't think it's as easy to see this directly and inversely proportional relationship. Okay, now I'm going to change my cart situation. My student texted me while at the grocery store and they canceled their tutoring session. So I got to relax and push my cart with 10 newtons again and wave at all my friends at the grocery store. It's such a happy place. That's why I'm smiling. But I get to shop and buy some more groceries. And when I bought more groceries, I added more things in. I put in some vegetables and some toilet paper and other things. And I doubled the mass. So now in my cart, I have 2 times the mass that I had before. But I'm still pushing with the same force because I'm not in a hurry. So what's that going to do to my acceleration?
It would be half.
It would be half. So let's prove it with our cute little rule of ones equation. If the force stays the same and the mass changes, then we're going to put in the 1 for the force and we double the mass. So that's 1/2. I don't have to do anything else. It just says 1/2. What if I was to cut my cut my mass down and decrease the mass? What would that do to the acceleration?
Increase it by half.
It would increase it. So if I cut my acceleration, or sorry, if I cut my mass into 1/3, and then I have an ugly fraction, 1/1/3, what does that mean for the acceleration?
So half.
It would be 1/1/3 is the same as 1 times 3/1, which is 3. So it actually inverses the fraction. So when that fraction's on the bottom, you flip it and multiply it. So that's where the word inversely comes from. Basically, whatever change you make to the mass, the inverse change happens to the acceleration. So if I quadruple the mass, 4 times the mass, then I make it 1/4, and that's what the acceleration would be. If I have a mass that is 1/5, I flip the 1/5 over, it becomes 5 times the acceleration. Does that make sense? So that's where that inverse word comes from. You're just inversing whatever the change is. So that's the conceptual stuff that you'll have to understand. And there's a lot of cool things that happen with this. If you think about, I love following the SpaceX rocket launches, and that's why your Google Classroom has a SpaceX rocket launch. I think it's super cool. This equation has some nice applications for that. If the rockets are providing a given amount of force as it's blasting off from the surface of Earth, and they're burning fuel, then the mass of the rocket as it goes up is becoming smaller, right? And so given a certain amount of force, rocket thrust that the rocket engines are providing, as the mass of the rocket decreases due to burning fuel, the acceleration is going to increase. So that's why they have to actually, once the rocket launches, they have to throttle down the engines a little bit as they're breaking through the sound barrier, just because their acceleration is so huge as they burn more and more fuel that it would actually damage the rocket until it just break through the sound barrier. We'll talk more about that later, but that's a good conceptual stuff. So let's talk now. I want to draw some pictures of different situations. I'm going to talk a little bit more about friction. Before I leave this behind, let me just erase a couple things around here. I want to talk about the units, because we are going to do math with this in a more traditional math way. I want to discuss, you know the unit for acceleration, right?
Yeah.
If I rewrite this, F equals ma, which is the other acceptable way to write the second law. The mass is, what unit are we using for mass? Have we talked about this yet?
Mass be no.
I don't think we've talked about this yet, have we? I get confused because I'm teaching 3 different classes, and one class did this stuff like the first few weeks. We're going to use mass in kilograms. In chemistry, you use grams, and physics, we use kilograms. So we're going to have kilograms, and then the unit for acceleration is good old acceleration, meters per second squared, very good. And then our unit for force is newtons, and that's the one we talked about last week. You know, we've been labeling things here. Newtons, thanks to Sir Isaac, who wrote all these laws, we honor him with the Newton unit. A Newton is equivalent to a kilogram meter per second squared. Thank goodness we don't have to write kilogram meters per second squared after every single force vector or calculation. We just rename it a newton. This is a little weird. In the last unit, everything kind of canceled out and worked nice. Like if you took meters per second, then you multiplied it by seconds, you got meters, and like things kind of, all the units were pretty and worked. This is a little strange. You'll get used to it then. So I just wanted to mention that before we moved on and I erased all this stuff. Okay, let's do some examples, and let's talk a little bit more about friction, which we have to deal with here on our planet all the time. Hold on, let's see if it's, it is. Okay, just want to make sure it's still recording. It doesn't ever stop, so I'm going to just finish it at home probably. Okay, we've covered applied forces, normal forces, friction forces. I'm gonna just do a couple of examples of and we've talked a good bit about this last week. Okay, so we've got somebody and they are pulling a wagon. Does our wagon have weight?
Yeah.
It does have weight. And so these pictures that I keep drawing over and over are called free body diagrams. So if you want to know more about free body diagrams, I know there's a lot of great videos online. If you want more like difficult practice with these and you want to work harder problems, let me know. I can always give you some of those because I got them. But that's what all these little force vector pictures are. So the weight and the normal are going to be equal. I'm going to say that this person is kind of short. I know I drew it at kind of an angle, but I'm going to go ahead and just say that he's applying a horizontal force, a pulling force this way. And I would like to say that the force of his pull is equal to, because he, let's say, is a very small and smallish person, let's say that he first pulls with a force of 10 newtons, and that our friction between the wheels and the pavement that he is currently pulling it across, let's say the friction is only 2 newtons. I'll squeeze it in there. So his pulling force is 10 newtons and his friction is 2 newtons. So when we look at our net force equation, I'm going to go ahead and say that this has it's got some rocks in there. I don't know. It's a kid on a mission. It's going to go do what my son used to do, sell rocks at the bottom of the driveway to cars passing by. He made a killing, by the way. I mean, I remember the mailman going, "You want $4 for gravel?" And what? He's so little, and he would just be like, "Yeah." And the guy would hand him, he'd give him a 5, and I'm like, "We have the nicest neighbors ever." And like, just paying him money all the time for rocks. So maybe this is what this kid's going to do. He's going to sell rocks. Okay, so if I look at my net force equation, net force equals mass times acceleration. The thing that, this is a very simple equation. It's this part that can be confusing. Most of the problems that we're going to do are going to be very straightforward, and it's going to have a force going one way and a force going the other way, and you're going to subtract them, right? Because if you have vectors going in opposite directions, they have a different sign on them, essentially. We would assume the pull to the right is positive, friction to the left is negative, and then we can subtract them. So that's what we're going to do for this net force part. We're going to take the pull to the right, and we're going to subtract the friction, and that's going to equal mass times acceleration. So we know both of these numbers, right? We know the mass of the wheelbarrow, so we can find out what the acceleration of the wheelbarrow is going to be. So let's plug those numbers in. We got 10 newtons, and we're going to subtract 2 newtons from that, and then we're going to put the kilograms in there, and we can find our acceleration. So 10 newtons minus 2 newtons is 8 equals 5a, and then we can divide both sides by what number?
You're trying the A, you say.
If we want to find the A, the acceleration, we need to get the A by itself.
So then you do the 5.
Yeah, so we need to divide 8 divided by 5, which is 1.6. So if we do 5, that goes away on that side, and then we have an acceleration of 1.6 meters per second squared. So that's really, that's easier math than the last unit, right? The kinematics equations are very challenging. This is a lot easier. And the only thing that can be tricky is if you're not quite given all the information and you have to be intuitive and this gets a little conceptual, then that can be weird. What does this acceleration mean, by the way? Every second
it's getting more pencil spinners.
Yeah, every second he's getting 1.6 meters per second squared faster. So that means eventually, if you think about a meter, I mean, that's a pretty good clip, right? The likelihood of him maintaining the pull of 10 newtons for any time longer than a second or two is small, because he would have to literally turn into Usain Bolt and like start running that. So he's probably not going to maintain a force of 10 newtons. In fact, what if he reduces, what if he starts going really fast and he's like falling over his little childish feet and says, whoa, this is dangerous, my rock wagon is going to run over me, I need to slow this down a little bit. What if he reduces his force, his pulling force, down to 2 newtons? So what's going to happen if he changes his pull and drops it back to 2 newtons? Is the wagon going to come to a screeching halt?
It would just be not telling.
That's right. So if he reduces the force to match the friction, which is something you think like, well, how is some little kid going to know that he's reducing his force to match the friction? He doesn't know. You don't know, right? I mean, we've all been kids. We've all pulled things. But you know instinctively when you're moving something or pulling something, if you're pulling it too fast, you can always reduce your pull or your push so that you're moving in a nice, constant, steady pace and you're not like falling trying to accelerate. So the only time you really need to accelerate like this is if you're doing some sort of crazy competition race of some kind. So if he reduces the force to match friction, then the net force will equal to 0, but he's still moving. And it's just going to be a constant velocity. So we do that kind of stuff all the time. One of the examples we were talking about, I think we were, but again, I'm getting confused with all my classes, was getting things moving. I'm going to talk about getting things moving a little bit. I'm going to erase this example. I'm going to have somebody pushing a refrigerator. Refrigerators are not very fun to push. They're heavy. My refrigerator is one of these that has the freezer on top. Okay. So, now I'm sad because I'm pushing my refrigerator and it's probably gross behind it and I don't want to see what's back there because there's probably dead spiders and lots of weird dusty stuff. So I'm pushing my fridge dough and it doesn't want to move. And that's because of friction. I'm going to tell you what the equation for friction is. But we're not going to do math with this. I just want to tell you what it is. So we can talk about it a little bit. One of the reasons why we need a normal force is because we use the normal force to calculate the friction acting on something. So what's the normal force equal to?
The weight of the object.
The weight of the object. So that makes sense, doesn't it, that the friction would be related to the weight of the object? Because heavier things are harder to get moving, right? So if we have the weight acting downward and we have an equal and opposite normal force acting upwards, in most cases, we're going to use the weight of the object to find the friction. What's this wackadoo thing right here? It's a Greek letter called mu. So, welcome, like William, meet mu. So this is a Greek letter mu, and it's a coefficient of friction. We're not going to do any math with this. I know this is a light green. I don't even think you can read this, maybe, in the bright sunshine. It's a coefficient of friction that it has to do with the interaction between the floor and the fridge. So if your floor is very smooth and your fridge is very nice and rolly or smooth, then it's a very small number. It's a little ratio decimal number. If your floor is some kind of rough concrete and your fridge has got jacked up feet on it, then it's going to be a bigger number. But friction, I just wanted to point out that friction is related to the weight, the normal force of the object. In this case, though, I want to talk more about the friction itself and what's going on up at the top with my guy and his push. I want to talk about the maximum amount of friction that can be present. Let's say that the maximum friction for this fridge is gonna equal 250 newtons. So here's the big idea, and this is gonna be on your CP page. The guy with the crates on the front, he's like pulling a crate. This is kind of what you're gonna be doing on that. If I'm pushing my fridge with a force to the right with a force of 100 newtons, is my fridge gonna move? It's not gonna move, because the maximum friction between the fridge that's not moving and the floor is 250. But here's what I need to find out. What is the friction? It's at rest, so we know that the fridge is at rest. It's not moving currently. What would the friction be? Would it be 250 or would it be 100?
That's a 250.
So the maximum friction is 250, but if I had a vector going this way, and it was that big, and it was 250 newtons, would there be a net force here?
Yes.
There would be, and then the fridge would run me over and I would be dead, and I would be so sad. So the friction is not gonna quite be 250 yet. It's gonna be 100. So it's like a mirror image. And then if I push with 180 newtons, my friction is gonna be 180 newtons. So the more I push, the more the friction is going to act back against me. That's why it's hard to get things moving, especially really heavy things. So then I go rest, I'm sweating, I'm so tired. Oh, I'm never going to move the fridge. And then I push with a force of 251 newtons. Now, what's the friction that's acting on the fridge?
250.
It would be 250. Is there a net force?
Yeah.
Yes. Okay, so finally I get my fridge moving. There is a net force of 1 newton. All it really takes to get the fridge moving is 0.00001 newton. So normally we say once the push matches the friction, you get it going, but I just picked 1 newton as a good example. Once I have that 1 newton of force in my favor, then the fridge will start to move. And then actually the maximum friction drops down, which is interesting. The highest friction is working on an object that's at rest. It's called static friction. And then as you move the object, kinetic friction begins to work, because now they're moving, the little surfaces are moving against each other. It's easier to keep them moving. So that's why once you get the thing going, usually then you can relax a little. You don't have to quite push as hard. So that mirroring thing happens. It's interesting. As you read the chapter and as you work on the conceptual physics problems, you'll start seeing some of the sort of quandaries that come up with friction and pushing and that kind of thing. So I just wanted to go